Hi guys, welcome to the Exploit Research Mega Primer Part 7. Now in this video we will look at how to overwrite the SEH chain and probably try and gain advantage through this mechanism. So hope you enjoyed the previous video, and as always please leave your comments behind so that I get to know more feedback about how I can improve. Okay, so let's do a quick recap of the concepts. As we saw in the previous video, the SEH actually contains a chain of exception registration records, right? And the whole idea is that these records are added dynamically as well as removed dynamically depending on where we are in the code path. At the very same time, regardless of how many of these new records are added or removed, the FS0 segment register always points to the start of the SEH chain, and this is maintained in the thread information block. So what happens? Well, when an exception happens, as we saw in the previous case, the operating system walks the SEH chain to check who can handle the exception. If an appropriate handler is found who can handle it, then execution continues based on what that handler is doing, else the default OS handler kicks in, right? So quick recap, if one or more of these statements are not very clear to you, I would request you to go back to the previous video and then come back here. So the obvious question which we did not answer in the last video was, who walks the SEH chain? It's the operating system, but exactly what happens? This is where we have a concept of the exception dispatcher. Now, I'll not get into the very low level details, but basically when an exception happens, the first thing the operating system running at ring 0 figures out is if this exception is a user space exception or a kernel space exception. If it is a user space exception, then it's going to go ahead and call the user space exception dispatcher by basically calling chi user exception dispatcher, right? Now, there's a long list of calls which happen subsequently, and this actually calls the RTL dispatch exception, which in turn calls the RTLP execution handler for exception. That actually calls the execute handler, which in turn calls the except handler 3. As we discussed, this is a generic handler which would be in applications compiled with Visual C++. So what happens in this except handler? Now this is the actual piece of code which calls our handler in turn, and it does this by actually figuring out the filter expression which we have mentioned in the exception handler in the scope table. And if basically the handler's filter exception returns saying that it can handle the exception handling goes forward. There are a couple of other steps which we needn't worry about, but it is good to know, which is unwinding and then actually going ahead and executing the handler for unwind and a couple of other things. Finally, the except block code is executed. So if I were to map this and take a very simple piece of code which a try except statement, then the filter expression we are talking about here is actually the filter we mention as argument to the except keyword. And if this returns saying that yes, this exception which has been passed to it, it can handle it, then we go ahead and also execute the code in the except block. If this expression returns saying, well, I cannot handle it, pass it down further in the chain, then the except handler will go to the next node or the next registration record, and then go ahead and do the exact same thing, right? So let's quickly understand a couple of things. This was a sample program which we had seen before, which implemented SEH, where we call function A, which in turn calls B, C, and which finally just prints a simple statement. Now, how does all of this look on the stack? Now, if you remember in the previous video, we had drawn a very large stack which contained all the stack frames for function A, B, and then C. In this case, we just kind of shortened it, and we are only looking at the final function C, within which we are in the try block. And this is how it would look like. You would have any local variable which we may define. then you would have the next ERR or the exception registration record pointer, and then you would actually have the exception handler pointer, right? So these two together, as we know, is the exception registration record. After that, you would have a couple of other things. As I mentioned, this is to some extent implementation specific, but let's keep the diagram simple for now. Now, as we know, the next ERR actually points to the record 2, which in turn points to record 3, and which in turn points to record 4. Now, one of the most important things you need to understand is that all of these records are actually there on the stack, as we saw in the previous video, within their respective stack frames of the functions in which they have been set up and may be called in the case of an exception, right? So basically this filter function which is there is actually what the exception handler is. So this exception handler 4-byte pointer points to the filter expression code which we are mentioning within the except statement. This is very important. Please note that. Now let's come back and let's assume that we currently had an exception in function C. So as we noted, we have that long list of calls which would happen, and that would eventually go ahead and call the except handler 3, right? And inside that, what it would do is now it would look at the scope table and figure out and actually take every single exception registration record and actually check whether the filter expression is actually telling it that it can handle the exception. So basically, as we mentioned, the filter expression is nothing but containing the pointer stored here, and this would actually in turn be pointing to the filter expression code which the developer may have mentioned. Now, what is the handler prototype for the for the exception handler, right? The prototype is, as we mentioned previously, except handler. Then we have a couple of things. The most important thing here is the establisher frame. Now, the pointer to the exception record as well as the context record dispatch context just gives a lot of more information. But the establisher frame, as we will notice, this pointer goes ahead and points back to the exception registration record on the stack. So let's try and understand what is happening. So currently, if you kind of notice, the exception handler is here, right? And our exception handler pointer is stored on the stack with the registration record. Now, it is important to note that when the CPU is going to go ahead and actually run through this exception handler, when the exception happens, right, then the exception, all the data here would be on the exception dispatcher stack, which is still running in the same context of the current thread. But it is important to note that this stack is on a different stack frame, even though they are located physically in the same process. So what happens here is something very, very interesting. Now, in the previous slide, we talked about the establisher frame. Now, interestingly, this establisher frame is stored, the establisher frame pointer is actually stored on the dispatcher stack. So currently, here is what is happening. We have an exception, because of which our whole list of the exception dispatchers have run. They figured out that they need to call the first filter expression. The first filter expression has been called, which points actually to the exception handler, right? Now this memory, this pointer here is pointing to the exception handler where EIP is currently positioned. Now at this exact stage, when we have not yet started even executing the first instruction in the exception handler, this is how the execution dispatcher stack looks like. And what we see is something interesting, is that the establisher frame is on the stack. Now, here is the most important part. It is at a fixed offset at ESP plus 8, which means there are just two 4-byte values on the top of the stack, after which we have the establisher frame. Now, as we mentioned, this establisher frame here, these 4 bytes contain a pointer pointing to the ERR stored on the stack. Right? This is very crucial and important, guys. So pay attention. This points back to the ERR on the stack. Right? So now let's go ahead and verify that this is so. So let's start with the demo. Now what we want in this case is to trigger an exception in the EasyChat server program so that we can trace the whole exception handler chain, right? So one of the easy ways which I figured to do that is EasyChat binds to port 80, and if there is already an existing program bound to that port, which means the port is not free, EasyChat throws an exception. So for that, what we'll do is I'll run the mini-share program which binds to port 80. Then I'll run EasyChat using immunity. Right? Let me run it. And now if you'll notice, as soon as I press OK, there would be an exception here. Awesome. So it says exception and it says enter shift F7 to pass the exception to the program. Right? Now, before we pass the exception to the program, we will need to understand a little bit about how the exception handlers are currently there on the stack. So one of the easiest things we can very quickly do is go ahead and figure out where on the stack the first exception handler is, which is referenced by fs0. Right? So if you notice, we actually went ahead and now we have the first exception registration record. First 4 bytes points to the next SEH record, and the next 4 bytes points to the SE handler. Now, if we go back to the slides, basically here is where we are. First 4 bytes points to the next record, and the second 4 bytes points to the exception handler code which needs to be run. Right, this one. So here is what we are going to do. Let's go ahead and set up a breakpoint as soon as the exception handler code is called. So for that, what we can do is we can just right click and actually say, well, follow in disassembler. So now if you notice, we are at this location 77EA04B8. So one of the first things we're going to do is add a breakpoint here. You can also hit F2. Okay, cool. So now, what is the second hypothesis we need to prove? The second thing which we need to prove is, as soon as EIP transfers control to the exception handler, which means we go ahead and start running, we are exactly here and about to run the first instruction, which is push EBP. At that point, this is how the stack would look like, where ESP plus 8 would be the establisher frame, right, which would go ahead and point back to the first ERR, or at this location, as we notice right now, which is 00E1FC9C. So let's just copy this to clipboard. Probably we can use something like Notepad to paste it so that we can analyze these addresses later. So here is what should happen right now. As soon as we pass control to the exception handler in the program by hitting shift F7, basically the exception handling dispatching by the kernel will start. And all of this would kind of go through, and in the absolute end, our filter expression will be called by the exception dispatcher. And basically, if you notice, this filter expression code is referenced by the execution handler as we've discussed, right? So this is exactly what we would be able to see right now. So let me go ahead and pass the exception to the program by hitting shift F7. Right? and then let's go ahead, run this program. And if you notice, the program is paused because our breakpoint is hit, right? And this is where we are just about to go back to the slides, execute the first instruction. EIP is currently pointing to the first instruction of the exception handler, and this can be verified if you notice the value of EIP 77EA04B8, which is exactly this point or the first instruction to push EVP. Now at this point, our other hypothesis was that the establisher frame pointing to the first ERR record is stored at an offset of ESP plus 8. Let's verify this. This is how the stack is looking at. This is the first 4 bytes, the second 4 bytes, and this is where the ESP plus 8 is. Now look at this value 00E1FC9C. If we open up Notepad, you will notice that this is the exact value which was pointing to the first ERR, right? Now the interesting thing is, depending on where we are having the exception, at that point, if probably we were into 1 or 2 more exception chains and we cannot walk through, then basically the dispatcher, the establisher frame would once again go back and point to their respective ERR at that point. So what this actually means is, well, whichever exception handler is currently about to run, basically at an offset of ESP plus 8, we would actually have the establisher frame which points back to that same exception registration record on the stack. Right? Is this understood? So once again, I'm just spending some more time here because it's a very important concept. Currently, we are just about to run the very first instruction in the exception handler. At that point, ESP plus 8 to 12, the 4 bytes here, is actually a pointer pointing back to the exception registration record. In this case, incidentally, it's also the first exception registration record, but need not be. We may have actually maybe executed a couple of more exception handlers along that linked list which we traversed. And in all cases, whichever exception handler we are executing, the establisher frame points back to that exception handler's ERR on the stack. Right? So at this point, well, we could allow the execution to continue and for various things to happen. But we'll go ahead and save that up for the next demo. So now here is what we will do. So we verified both of these. Now let's go a little bit into the slides to understand what can happen next. Analyzing the two stack frames. So one is the program stack and the other is a dispatcher stack. One very important thing which you need to note is both of them are actually on the same stack. It is just that these are two different stack frames, right? Now at this point, let's move ahead and see what happens. Now here comes how can we exploit an SEH condition. What if? Now let's assume that the exception handler has 3 lines of assembly code, and these are the 3 lines: pop EAX, pop EBX, return. Right? What would happen? Now when EIP goes ahead and executes the first instruction, pop EAX, what would happen on the dispatcher stack? This 4 bytes would actually be taken out and would be stored within EAX, and ESP would kind of go down and adjust itself. Actually, it would go from low memory towards high memory. Never forget that. And this was what would happen. The value goes off, ESP adjusts itself, right? So now when we are, let's actually go ahead and also simulate this in our program. So here is what we are going to do. What we said is at this position we have 3 instructions: pop EAX, pop EBX, return. Now the beauty is you can just right click and hit assemble, and you can change the instruction which is currently there. So let's say we type in pop EAX as the first instruction, next instruction as pop EBX, and the third instruction as a return. right? So here is where currently EIP is pointing to. So let's go ahead and run the first pop. What would happen? The first value on top of the stack would be popped and placed into the EAX register as expected. Now we cannot do a one-to-one between the presentation and the actual demo. Now the next instruction, pop EBX, is going to take out one more record and the stack will adjust itself. And then the third instruction, return, would go ahead and pop the establisher frame, which is the 4-byte pointer pointing to the EIR, and store it within EIP. We know the return instruction is going to pop the next 4 bytes of the stack and put it inside EIP. And hence, this is what ends up happening. Now EIP, containing the value of the establisher frame, points back into the stack to our ERR. Of course, the stack is going to adjust itself as well. Let's verify this. Let's go one more instruction which will pop EBX. And now if you notice, this is the value, right, which is the establisher frame, as we can see here, which is just about to be popped into the EIP register. So closely look at the value of the EIP register. It is going to be modified to this value, which points back into the stack, and we would notice that in just a minute, right? So this value is going to go into EIP now. Perfect. If you notice, EIP currently has the value 00E1FC9C, which is the actually a pointer to the exception registration record. Beautiful. And as you can see here, EIP has been positioned to this position where we are pointing currently to the exception registration record, whose first 4 bytes are pointed to the next SEH record as always, and the next 4 bytes are our SE handler, right, which we just kind of executed and came back here. So let's go back to the presentation to understand this better. Right? So what do we have here? Now EIP is pointing to the stack. Now from our buffer overflow basics, we understand that if EIP points back to the stack, we can run code on the stack. So basically the first 4 bytes from the beginning of where EIP points to is actually the next exception registration record which is being stored. Now that is just a pointer, but interestingly, because EIP points to it, EIP will interpret anything it sees from that location as command which it has to execute. Now the whole point is we could be placing anything there, but there is a catch. Now the catch really is that we only have 4 bytes, because note that we really cannot write any instruction into the next 4 bytes, because the next 4 bytes is actually the exception handler, which we would ideally want to point to the pop ret instruction set. Now in this example, though we had taken pop EAX, EBX as special cases, basically this is pop any register or pop any other register and then return. And this is where in SEH attacks we actually call it the pop ret sequence or the PPR sequence very popularly, right? So now the question comes, how do we go ahead and corrupt the next EIR? Right? So let's come to this part. Okay. So now how are we going to go ahead and overwrite the next ERR and exception handler? There are 2 things we need to do. We'll come to what we will overwrite the next SEH handler record with. Exception handler, we know we need to override that with a pop ret sequence. So this is where the buffer overflow vulnerability comes back. And basically what we can do is we can overflow probably some array or something which may be a local variable in the function C, and that would go ahead and overwrite everything including the SEH chain. right? So we've already verified that the pop-pop ret instruction sends control back to the next ERR location. Now let's go ahead and figure out how to cause a buffer overflow in the EasyChat program, right? And with this we will end this because it's already around 25 minutes, and what I figured is that very long videos nobody may actually have the patience to watch. So in the next video, after this we'll look at how to actually exploit it. But now let's show that we are able to overwrite and corrupt the SEH chain. So for that, let's quickly go ahead and do the following. Let's of course first close this, remove mini share so that we can free up port 80. And then let's open up Immunity once again, and let's go ahead and run the EasyChat program. Right, so it's up and running. Now the next thing we'll do is the exploit link which I had given you previously. If you kind of very quickly go through the exploit for the EasyChat server program, let's forget about all of this for the time being. All we are really looking at is the following. It is making an HTTP request, and basically this is the URL it is requesting for, where buffer and basically the username and the password field seem to be vulnerable. And this is where we are passing our buffer, well, with all the garbage, the jump instruction, PPR and other things. So what that basically means is that either the username or the password, or maybe both the fields, have the overflow bug in it, right? So let's go ahead and quickly write up a program for this. Right, we want to connect to port number 80 where the HTTP service is running, so it's a stream socket. After that, we want to connect to that port and the IP address, which will be a command line argument. Then we go ahead, construct our buffer. Right, so in this case, we're going to have a get statement. After that, let's go ahead and figure out what is the exact URL. We could as well just take the URL. Note it's an HTTP request, so we'll have to add the delimiters ourselves, right? So let's do the following. Why don't we just break this up into different ones? Buffer. Actually, you know what? I should just paste this here and then break this up accordingly. So what we can actually do is, well, we have the username field here, and then actually password, why don't we just feed something static, let's say test. It should mean we would not require this anymore. So this seems fine. We have all the arguments and everything given, and because it is an HTTP request, after this we would have to have an HTTP version along with the delimiter /r/n, right? And at this place is where we are going to add our buffer. So right now let's just pretend that we really do not know how many A's we need. We'll just pump our usual 2000 in, and then let's just go ahead and send buffer. And then let's close the socket. Right? Does it look okay? Seems okay. Let's just run it and have a look. Now what we need is the IP address of the remote system, which seems to be 101. And let's send the data. And if you notice, there was a exception violation. But the interesting thing is EIP has not been overwritten with our A's, and this is the classic case in which we would like to use an SEH based attack. To verify that the SEH handler chain has been overwritten, you can go to SEH chain and you would notice that the SE handler is currently pointing to 41, 41, 41, 41. Of course, the next one is obviously going to be corrupt as well. Let's look at where the overwriting has happened on the stack. So if you notice, this is the pointer to the next SEH record basically, as well as the SE handler. Both of them have been corrupted, and this is the reason why the chain has been broken, because immunity is not able to figure out well where this SEH record is actually pointing to, right? So I guess that's all for this video. In the next video we will look at how to now go through the entire route of writing an exploit for the SEH based error condition. So please leave your comments behind. This has been a long video. Hopefully you enjoyed it.